So just a quick recap of where we are. So we are in the surface contact region. Alright, we have cleared all this already. Alright, and we'll talk about the. So previously we talked about the type of stresses on the surface and the plasticity understanding. So we'll talk about how to calculate the stresses now. Alright, and the slides over here we'll talk about surface single contact, alright, and two curved surfaces. Okay, and you need to know this concept of the Hertzian stresses, alright, that arise from contacts of solids. So what are the difference between single contact and two curved surfaces? Alright, let's take a look. So imagine you have this piece of hard material which is harder than this floor, alright, this surface. So if I were to put it over here and then I drag all the way, alright, you see? So I kind of drag all the way, and this is called a single contact because there's only one thing that is contacting the rest of the stuff. Okay, and this is called a single contact method. Nonetheless, if you were to impress it onto the thing, and then if the floor over here were to indent, alright, this is also called a single contact. Alright, what about the double contact? Alright, maybe it's not double contact, I should call it the two curved surface type of contact. So the two curved surface type of contact is talking about, give me a while, when the bearing is moving or when the bearing is turning. Okay, so what does this mean? Alright, so previously, right, this thing over here is moving. Alright, this thing over here is moving. There's only one thing moving. However, if you think about it, the bearing over here, in fact, there are two things that is moving, right? To a certain extent, it seems like two things is moving. Okay, so this is the ball, one of the ball in the ball bearing, and then this is the rotating thing. Alright, so you rotate this one because this is only one thing that is moving. Alright, this thing over here will be contacted, and this is called a single contact. Alright, but however, when you rotate this one, alright, these surfaces over here will also move in this direction. I mean, this thing over here, it will be rigid. Alright, you will not move. Alright, this thing over here will not move. However, this thing over here will turn. It will turn. Alright, and due to this shaft that is turning, and also due to the friction that is occurring at this point. So there is this point is turning, and this point is also turning. So it's caused by two form of forces, and therefore it's called the two curved surface type of contact surface, because it's curved also. Alright, and this is most applicable in gearboxes and everything. Alright. Therefore, I think in this video I will talk about the single contact, or if I got time, I can evaluate more on the double curved surface. So the single contact, right? The stresses R is equals to stress max times this equation, where this thing over here, A, is your impression radius. I may show you, yeah, impression radius. So what is this impression radius? I took quite a while to think about it, and I think I may found the reason. Okay, so maybe I should use a new picture. Give me a while. As I say, if I have a certain material, okay, and then if I have this hard material over here, this is the ball, some balls lah, okay, and if I were to press it down, it actually go through the material already, right? It actually indented the material and causes a impression. Alright, you impress something. Or it's not that I impress you because I handsome or I pretty or whatever, but I impress onto the surface. So I somewhat like I press onto it. Okay, so therefore this impression will cause a certain radius. So after you impress, you take out this material, you'll get to see something like that. Alright, so this thing over here, if you have an imaginary circle, okay, and this is the center point, this is the impression radius, which is shown over at this side. Okay, hopefully this is clear. Alright, and therefore the R max is equals to A, or the radius max over here, I think, okay, is equals to A. And hopefully this is clear. I think I may be wrong, alright, but I think this sounds logical than my previous perceptions of it. So my previous perception, okay, so this is the first perception, alright. So this is the first thing that I talk about impression radius. So the second thing that I talk about in impression radius is this. Alright, if you were to impress onto this surface, alright, this thing over here is the radius of the material. Alright, but if you were to impress, you may have another radius A. Alright, that is go towards the impressed surface. Alright, so this is the second one that I think, but after going through a lot of stuff, I believe this one will be better explanation. Nonetheless, I'll leave you to think about it. Alright, so therefore let's continue with the equation. Alright, so they are trying to find stress R, which is at any radial distance from the center of the indented impression area, like a chimp. Alright, so the stress max is over here. Alright, so take note of this circle. Alright, this radius over here is different from the radius. Alright, the hard material is called the hard rider. So over here, this radius is different from this radius. This radius comes from the indentation over here. Alright, but this radius comes from the material itself. So from this indentation, there is a certain radius. Alright, and therefore there will be a certain stresses, alright, acting on it. So this will imply that at this particular point, if you have a certain invisible stuff, give me a while. Right, this is the radius. Alright, so there will be a certain stresses, alright, acting upon here. Okay, so they are looking at this particular point, because if you were to press an indent over here, alright, this point over here is going to restrict the movement of the whole hard material. Right, if you were to try to push this apart, or maybe to give me a while, if you try to move it around, it's just all the way stuck over here. Right, stuck all over here, and this is why these 2 points over here will somewhat determine the radius of your so-called the one that you are looking at. So this is somewhat like an imaginary radius. Alright, where you imagine that the stress will add upon within this radius. Alright, and this point over here, somewhat there will be not much of a stresses that is occurring. Only at this point is kind of something that we are looking at. Okay, so this is quite of a in-depth stuff. Hopefully you can understand. So if you were to come back here, these are the stresses that is acting upon from this imaginary circle, or this imaginary circle. Hopefully you see this. Yeah, this imaginary circle. So the stresses from the center point, alright, these are all the stress R. Alright, where the maximum is actually at this point, stress max. Okay, hopefully this is pretty clear. Now to calculate this type of stresses that is acting upon it. Alright, so I also don't know why they want to find this, but at least you know something. Alright, at least I find it quite logical now, instead of just now my another explanation. Alright, anyway, yeah, burping. So I may need to know my stress max. I also need to know my indentation radius, impression radius. Okay, A. Alright, hopefully you already know where the hell is A. So this thing over here is A. Okay, this is the radius, or at this point this is the R max, the maximum of the radius, so to speak. But anyway, let's come back here. Alright, so you will need two things. You need first the stress max. Second, you need to find A. While the radius is the one that is the material, the hard material, the rider. The radius is really given to you, so you don't need to find anything. Okay. Sorry, I take back my word. In case later on I'm gonna redo the video again. I take back my word. This R over here is not the radius of here. Alright, it's not this one. This is capital R. That one is small capital R. So what is this small capital R? This R over here is the radius that you want to look at. Alright, it's like now you are actually doing an equation. Oh yeah, this equation over here is something to write into a computer. Alright, where you talk about SolidWorks and things like that. So for example, this is the radius that we're talking about. For example, this one. Okay, so the maximum of it is A. Right, this is the indentation radius that we talk about it. So if I draw it like that, so this is the indentation radius A. Alright, so if I have another radius that I want to look at, I'm actually keen about looking at this particular point. What is the amount of stresses at this point? Alright, it's at this point. This is the center point. Alright, so this at what is the amount of stresses at this point. Alright, and therefore you're going to sub in a particular r. So this r is the variable that you're going to put in. Okay, hopefully you're clear. So if you choose another r, if you want to look at particular what is the amount of stress at maybe at this point or at this amount of radius, alright, then definitely there will be a different stresses already. Instead of this black color one is all the way extends to here. So you're looking at this particular point. So the stress at this r is variable. Alright, you're going to choose your radius all along. Hopefully this is very clear. If you don't understand, you flip a few minutes ago and then you refer back and then you watch again and watch again. Hopefully it's quite clear, or you can draw it out. So the key concept over here, if it's confusing, is that this radius is the indentation radius A. Okay, it's an imaginary radius. Hopefully you are clear. Or it comes from your hard material. It comes from your hard material over here. This is the hard material, right? Sorry, what am I drawing? Damn it. So this thing over here is the hard material, right? So the indentation material is actually this one. The indentation circle. Sorry, how am I talking? A bit blurry already. Check. So this is the indentation radius, the imaginary radius, where you look at it, or where you observe it, and you predict the amount of stresses that is acting upon it. Alright, so hopefully you're kind of clear of the equations, so that it doesn't confuse you in any of the form. So you want to know your one, and you want to know your indentation radius, and this is the radius that you want to this is the radius that you want to look at. If you put in this radius, you'll know the amount of stress at the particular radius. Alright, so hopefully this is all clear. And take note of that this thing, if r is equals to 0, so if there is no radius, alright, it is the maximum. So this point over here is the 0, right? So if at this point, this is the maximum stress, right? Because you're traveling across this particular sector. Alright, so the longer you are, the more higher stress. Alright, this is why we're talking about the different stresses at different points. So this pi or r, you have a different stresses which is somewhat lower. Okay, so I hope that you're kind of clear. So if you were to look at SolidWorks, every time there are different colors, right? So the different colors comes from all these things lah, the different amount of stresses at different points. Alright, so maybe you'll know that, oh, maybe this is the lightest. So along the way, this part over here will be the highest stresses all along, that of thing. So hopefully you are kind of clear of that. Alright, and yeah, so in order to find this stress max, alright, in order to find stress max and this thing, you will need to find your A. Alright, so therefore this thing is the most important thing, your indentation radius, impression radius, damn it. Your weight over here, this is the weight lah, precisely. So this R definitely is the dude over here. Alright, this capital R, the radius of the indented material. Alright, and the E is the equivalent Young's modulus. Alright, at the contact location, at the point where you contact to the, if you are this material, at the point where you contact to the surface of it. So there will be certain Young modulus you are looking at. Alright, and it's dealing with the Young modulus in the 1 and the 2 direction. So it is the 1 x-axis and the y 2 direction. Nonetheless, you may have different reference frame, or you may look at this point. Alright, this is the 1, this is the 2. So it depends on where you look at. So take note of that. Alright, so this equation you need to know. Alright, it's not provided in the exam, so you please remember this thing. While this thing over here, the lecturer says he's providing, but in case if you want to memorize, you memorize yourself. Alright, and V is the Poisson ratio of the material. Yeah, good question. So the question is that, do you use the Poisson ratio of the ball or the surface of the material? Okay, I'll leave you to think about it. In the future, if I have something, then I'll update over here in this video. Okay, so nonetheless, you just keep it in mind that this equation you need to memorize. Alright, so once you get this, you will find your equivalent Young modulus. I'll make sure that it's 1 over E. So you want to calculate E, then you're gonna switch the mathematical values here and there. Alright, so E, once you get this E, you can sub in over here. Alright, and you can find your A. Alright, so it's very important. Alright, now once you find your A, then you can sub in into your stress max equation. Alright, so this A over here, as you can see, this A, once you get this A, then you can find your stress max, which is all the way back to here. Alright, so once you find this A, you can find this, and you can find your stress max, and eventually you can solve for the stresses at the particular radius that you want to observe. Alright, so nonetheless, you can also have an alternative way to find your stress max. So it was done knowing that the maximum shearing is about 1/3 of the maximum stress. Alright, the maximum shear stress is 1/3 of the maximum stress. Okay, so you need to know where is the maximum shear first. Once you get this maximum shear, you need to determine. Then you can use this equation to find your shear max, and then you sub it in back to this equation. Okay, so it happens that they don't give you certain information, or at least you need to know how to calculate the rest of the stuff in a way. Alright, so there's a few ways lah. Alright, so the first way is that they give you information like this equation, the what's that called, the Poisson ratio, the Young modulus, and you calculate backtrack to get this A. Alright, and then once you get this A, you sub in, and then what am I talking? Give me a while. So the first method, alright, is the one that we talked about just now. Okay, this, you find your A, and then eventually you can find out this one, and then this one. Okay, the second method is that you find your stress max first, where everything regarding the A is not given. So they'll ask you to find your shearing. Once you find the shearing, you can find your shear max. So using this shear max, then you can know the A value, and then once you get this A value, you can sub in back, including your shear max. Then you can find this thing. So there is two methods. Okay, hopefully this is pretty clear. A bit shaky already. So yeah. So let me see. So the maximum shear, alright, the peak shear stress, alright, is at a distance of 0.5 to 0.7 A. Alright, so you know that this is A. You will know that particularly, alright, the shear stress will be somewhere in between, somewhere over here. Alright, or somewhere over here, 0.7 A. Okay, so you need to know that this is the thing, and this is very important. You need to memorize also, and which is pretty easy to memorize, so I don't need to explain much. So this is where you find your maximum shear stress lah. Alright, so yeah, things like that. I don't know lah, think about it lah. You think about it yourself lah. So all in all, if you want to find your shear max, then you find through this method. Alright, or in other words, 3 times shear max, actually 3.2 or some 3.2, because if you bring this down, it's about 1 divided by 0.31 is 3.2 something. Alright, so it's 3.2 shear max is equals to stress max, that of thing. Okay, so therefore all in all, right, this page that what I've been talking along all this equation, I mean this page, right, I mean this video is talking about this page. Alright, it's talking about page 17. Alright, single contact Hertzian stresses, where it talk about stresses which arises from contacts of solids. Alright, so later on we'll talk about the two curved surface. So there are different Hertzian stresses at different scenario. So the first scenario is a single contact, which is what we have said in the first video. I mean in this video. And then next video we'll talk about these things, and the Hertzian stresses will be different equations. Alright, so I shall see you there. Bye bye.